So, hello everybody. I wanted to go over chapter 4, this homework this week. Um, Chapter 4 is a little bit about um, velocity addition, angular acceleration, um, and finally, uh, some projectile motion. So, as we go through these, I'll try to highlight the equations that matter and whatnot. In this first problem, we're talking about velocity addition, but we're also really talking about two-dimensional motion. So what we have is we have a 100-meter wide harbor, and we have a current flow to the east of 2 meters per second, and we have a kayaker that can paddle at 3 meters per second. So if we look at this, what we're trying to do is we're trying to get across a river or a harbor that is 100 meters wide to the north or positive y-axis. That water is moving to the east or along the x-axis at 2 meters per second. And in the x direction, positive x-hat direction. And we know that our kayaker can paddle with a velocity relative to the water. So I'm going to put kayaker relative to the water at 3 meters per second in whatever direction she wants to go. This is actually the velocity of the river versus the ground, and she wants to go directly north. So in this problem, we're told that what direction or he needs to paddle to travel straight across. The velocity of the kayaker versus the earth is going to be the velocity of the river over the earth. Well, let me actually do it the other way. The velocity of the kayaker versus the river plus the velocity of the river versus the earth. So if you cancel the river subscripts, you get the velocity of the kayaker versus the earth. Now, there is x and y motion here. So in the x, it'll be the velocity in the x, and there is in the y. And all we want is we want initially to know what direction they should point in order to travel straight across. Another way to think about this is as he tries to paddle straight across to the north, the river is going to be pushing him to the east. He's going to need to paddle at some angle to the x-axis so that his x velocity, so the velocity of the kayaker, the x velocity cancels out the velocity of the river, and then whatever's left over in the y direction will be his speed straight across. But we need to know what direction that is. And how we do that is we know that in the x, so he's going to have to paddle at some angle, kayaker versus the river, at some angle in order to cancel out this velocity. So these two velocities will be 0. They have to equal 0. So let's start there. If we know that 0 is the velocity of the kayaker versus the river, and the velocity of the river versus the earth, we know these two things need to be 0. In the x direction, the kayaker can't have any velocity. Now we know that this is 2. This is 2 meters per second. And we know that since this is 0, the velocity of the kayaker versus the river has to be equal to the velocity of the river versus the earth with a negative sign. Move that over, subtract it from both sides. So we know that this has to be -2 meters per second in the x-hat direction. that'll be the velocity of the kayaker versus the river. In order to find the y, now, we know that the velocity of the kayaker versus the earth is the velocity in the y direction, is the velocity of the kayaker versus the river in the y, plus the velocity of the river versus the earth in the y, but this is 0. So we know that that'll be, the y will just be whatever the y is. Now we need to think about a little bit of what we know kayaker versus the earth, versus the river, is going to be -2 meters per second in the x-hat direction. And the velocity of the kayaker versus the river in the y direction is going to be the velocity of the kayaker versus the earth. So we need to figure out what this is. We know that the velocity of the kayaker versus the river is going to be somewhere here. We also know that B, kayaker versus the river, has a magnitude of 3 meters per second. That is how fast he can paddle. And that is equal to the square root of the velocity of the kayaker versus the river in the x squared plus the velocity of the kayaker versus the river in the y hat squared. Or another way to think about this is this thing, the magnitude is the x component squared plus the y component squared, square rooted or squared. So v of y squared, which is kr squared, is equal to the magnitude squared minus vx squared. And if I take the square root of that, of both sides, I can find the component in the y direction. So this is the magnitude of v is 3 squared minus the magnitude in the x, which was -2 squared. So this is 9 minus 4, or the square root of 5, which is square root of 5 is 2.24 meters per second. And now the last thing I need to do is to find the direction. I'm going to find it relative to the x-axis. And the direction of v relative to the x-axis is the arctan of vy over vx, or arctan of 2.24 over -2. That negative is going to be important because our calculator is actually going to give us a bad angle. It's going to give us an angle between 90 and -90, and we actually need it to be somewhere between 90 and 180. So arctan of 2.24 divided by -2 is -48.2 degrees. That's down here somewhere. It's a straight line. This is -48.2 degrees. So what do? We add 180. So plus 180, and I get 131.8 degrees. Add 180, quadrant 2. So our kayaker should point himself 131.8 degrees. Now, they want the degrees north of east, however, and that means how many degrees north of east? So they rounded to 132. North of east means start at the x-axis and take your angle in the positive direction. All right. How long will it take him to cross? Now we know that v in the y for him was 2.24 meters per second. And we know that he has to travel a distance of 100 meters to the north. V is change of y over change of t. or the change of t is the change of y divided by v. So that is 100 divided by 2.24, 100 meters divided by 2.24 meters per second. Takes them about 44.6 seconds, a little more than a minute. They got 44.7, they got 45. I would go with 45 seconds, round it up to 45. My rounding's a little bit off, probably because I didn't take the Vy all the way out. This is really 100 divided by square root of 5. So 44.7 is actually what I meant. Let me do this just to make sure you have the right answer. Okay. But the main takeaway here was you had to, one way to do this is to use velocity addition with subscripts. Then you had to realize that after he begins to kayak, he should have no x velocity. So his velocity in the x direction needs to completely cancel the current of the river. Once you have that, because you know the magnitude of his total velocity from Pythagorean theorem, you can find Vy using the magnitude squared minus Vx squared, and then take the square root. And then finally, to find the angle, use the arctan of Vy over Vx. It's a little bit of a hassle, but that's about as hard as it gets. Okay, so now we need to talk about rotation. We previously talked about uniform circular motion, but now we're going to talk about just normal rotation. And when something rotates around a solid object, say a disc or a ball or a wheel or whatever, we can use what's called the rolling without slipping approximation. And that means that the arc length, this distance, is delta s, and that distance subtends an angle theta. We assume that the radius stays constant, so we have delta s is r delta theta. Theta has to be in radians when it's not in an argument. It's not part of sine, cosine, tangent. If it's out on its own, it has to be part of, or it has to be in radians. Radians are real numbers. It cannot be in degrees. From this, if we take the time derivative, ds dt is v, and d theta dt is something that we call omega. Finally, dv dt is something that we call a, and d omega dt is something that we call alpha. Now, in this equation, when we look at this equation, or these equations, what we get is we get that the arc length s is related to the angle. The velocity is related to omega, and the acceleration is related to alpha. But to be clear, as you're going along around a point, right here, s would be the change of arc length. V would be tangent to the path. Omega is actually the same at every point. V will actually be different depending on your radius. And that's because omega is the same for every point, but V changes based on where you are. This guy is at, say, r to the half. This one's, say, at r. So V2 would be r to the half omega, and V1 would be r omega. V1 has to be faster because it takes longer to go around. On the outside, you have to cover a longer circumference in the same amount of time. Same with A. This A we're talking about is not radial, it's tangential. This V is tangential, it's along the path. Alpha is the same for every point. A changes based on where the point is located. Next up, so we have S is r theta, V is r omega, and A tangential is r alpha. Now, the period, which is 2 pi r over v, that's how long it would go around a circumference at 2 pi r, divided by its velocity. But if we look, v is actually r omega. So if I plug that in for r omega, what I get is the following. I get 2 pi over omega. So t and omega are related. T is equal to 2 pi omega, which is also, omega is something called an angular frequency, but the actual frequency is 1 over omega. So this is also 2 pi f, if we're given that. Lastly, one rotation is 2 pi radians. So if we need to find the number of revolutions, one rotation or one revolution, it will turn through an angle of 2 pi rads. Our delta theta will be 2 pi rads. One way to think about t versus f, okay, t is equal to I feel like I did something. Yeah, why is that being weird? Bum, 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 bum. Yeah, I'm dumb. Let me go back for a minute. So t is equal to 1 over f. So yeah, it's just being weird. Sorry, guys. So omega is equal to 2 pi f, and t is equal to 1 over f. Now, how you relate frequency and period is the period is the number of seconds in one revolution or one complete rotation. The frequency is the number of rotations in 1 second. They're inverses of each other. So if you're given a frequency in hertz, and frequency are in hertz or Hz, which have 1 over seconds. If you are ever given a frequency, it's the inverse of the period, and it's related to omega. So in these problems, you usually are either trying to find omega or you're given omega, and then you can find the period and whatnot. It's not hard, it's just how you relate these variables. So an old-fashioned record player rotates at 45 RPM, and we want to know the angular velocity, omega, and the period. So t and omega are related in the following way. Omega is rads per second, and RPMs are revolutions per minute. So we need to turn this into radians and seconds. In one revolution, there are 2 pi radians. And in 1 minute, there are 60 seconds. So if you do that, the minutes cancel, the revolution cancel, and you get rads per second, or 2 pi over 60. So RPM to rad per second multiplied by 2 pi over 60. That's the conversion. So we're told 45. So 45 RPM times 2 pi over 60 rad per second over RPMs. And we get 45 times 2 times pi divided by 60 is 4.71 rad per second. And that is our omega. Our omega is 4.71. To find the period, it's 2 pi over 4.71. So 2 times pi divided by our answer, and we get 1.33. That means it makes 1 revolution every 1.33 seconds. And that's it, okay? This problem is just convert RPM to rad per second. That gives you your angular velocity. Find the period by dividing 2 pi by your angular velocity, omega. 3. Second is something called a rad, and this is uniform circular motion. In uniform circular motion, stop it, Puff. In uniform circular motion, we assume that we are going around in a circle with constant velocity. While we do that, because we're constantly turning to the center, we have a radial acceleration. A rad, the radial acceleration, is equal to v squared over r. We already know that. Okay, so v squared over r. If we want to convert this using omega is v over r, or v is omega r omega, we can turn this into r omega squared over r, or r omega squared, should we need it. We don't need it in this problem, but just be aware. A tangent is r alpha. A radial is v squared over r, or r omega squared. They are different. So this would be a tan, this is a rad, and the actual A is at some angle between. Don't confuse those two. But in this problem, we're talking about a rad. So the centripetal acceleration is a radial, and it's called a radial because it points to the center. We're told, oh, and lastly, since a rad or a centripetal is v squared over r, and t is 2 pi r over v, we also get that a rad is, if we solve this for v is 2 pi over the period, r over the period. We can plug this in for our v squared. We would get 4 pi squared r squared over r from here over t squared. So we have, these equations are basically uniform circular motion or centripetal or a radial, whatever you want to call it. We're told that a rad is 1.5 times free fall acceleration. So we're told that our radial or centripetal, whatever you want to call it, is equal to 1.5 Gs, or 1.5 times 9.8. What radius turn if the Falcon is flying at 25? So we're told v is 25 meters per second. And this is meters per second squared. So a rad is v squared over r. Multiply both sides by r. Divide both sides by a rad, and you get r is v squared over a rad, or 25 squared over 1.5 times 9.8. And that'll give us the radius in meters. This is meters squared over second squared over meters over second squared, and we'll be left with meters. So 25 times 25 divided by 1.5 times 9.8 is 42.5 meters, 42.52 if we want. 42.5 meters. That is the biggest turn. They went with 43 that it could make. And that's it. That's all you have to do on this one. A is v squared over r for a radial or centripetal acceleration. You were given v squared, you were given a rad in terms of g. All right, and so now we're on to the meat of this. Before I move on to this one though, I actually want to go to the, back to a couple of radial. So we have three, whatchamacallits, 3 or 4 projectile motion, and we'll come back to it. So one of the things that when we use our theta, when we are rotating, our theta kind of takes the place of x, and omega kind of takes the place of v, and alpha kind of takes the place of a. We can go back to the original x equations, if you remember, are constant. If we were to say that d theta is alpha dt, because alpha is d omega dt, we were to integrate these from 0 to t and from omega initial to omega final, etc., And then we were to do d theta from theta initial to theta final and omega dt from 0 to t, we would get the same set of constant acceleration, but with different variables. These are actually quite easy because we only have this, and these are constant terms and blah, 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 blah. But it's much more like free fall than like projectile motion. So you'll have the following. And they're exactly the same as the constant acceleration equations, but you just have to change your variables. And you may actually use this one. So we have these. Now looking at this though, normally we would have omega t, and if we looked at that, the idea there should be that if this was the slope of omega versus t should be, if you think about it, it should be that slope, omega over t should be alpha. This should be alpha, but this is actually t squared in this problem. It's a little weird. This is actually a harder problem. And I started to do this in class and I realized, wait, I forgot this is one of those weird ones. So this graph is actually omega versus t squared. And we're going to have to do a little bit of work on this just to make sure that we understand what we're actually looking at. Now in this, a gyroscope is a little thing that spins in a circle. And we're told that every half of a second they measured omega and they found it to be increasing at this rate. And so they plotted a best fit line. Now at t equals 0, this in a linear, so in a y is the slope of x plus b, if you graph this y versus x, then your slope is whatever the line is, and b is wherever x is 0, y is b. So when time is 0, that is going to be where our angular velocity is, where this line hits, and that is 32. That is what that tells us. So this is a little bit about graph. That's 32. However, then we want the angular acceleration at a time of t is 0.5 seconds. Our line is omega of t is, the line we're given is 42 plus 32, but the x in our problem is t squared. So this is t squared. Alpha is the time derivative of omega t. Taking the time derivative of this, the 2 comes down and I get an 84 times t. There's no derivative of this. If I take that time derivative when t is 0.5, I get that alpha when t is a half a second is 84 times 0.5, or half of 84, which is 42. And since this was rads per second, it's rad per second squared. Okay. Just that's what your, those are your units. Okay. We can also see though that the slope is 42 along here. That slope is 42, which happens to be what our angular acceleration is. What is our angular acceleration? Well, it speeds up. So had we chose 3 seconds, we would have gotten an angular acceleration of 84 times 3. Alpha is actually increasing because this is omega versus t squared. This slope is not alpha. Just so you know, that slope is not alpha. All right. Finally, how many revolutions does the gyroscope make between? So we want to know the number of revolutions from t is 0 to t is 0.5. So we need to find the time between these two. And how do we do that? Well, the change of theta is d theta, and that integral is equal to the change of theta. We need to find the number of radians. But that integral is equal to omega t dt, okay? So we need to integrate from t is equal to 0 to t is equal to 0.5. We need to integrate our function. And this was 42 t squared plus 32 dt. And then go from 0 to 0.5. Integrating this becomes 42 t cubed over 3 plus 32 t. Now, we don't need to worry about the negative part. What we normally do is put in 0.5 for t and then subtract 0 for t. We just need to calculate for t is equal to 0.5. We're not going to be done quite yet once we get this number. So 42 divided by 3 times 0.5 times 0.5 times 0.5 plus 32 times 0.5 is 17.75 rads. But what they wanted us to find is how many revolutions. And in one revolution, there are 2 pi rads per revolution. So you need to divide your answer by 2 pi. So 17.5, 17.75 divided by 2 times pi gives you about 2.82 or 2.83 revolutions. So this one is all about, and they just went with 2.8. This one's all about, because it's omega t squared, which is why they made it omega versus t squared, you have to take the derivative to get alpha. And because it's omega versus t squared, you have to take the integral to get theta. And so I just want you to remember that alpha is the integral of d omega dt, or alpha is the derivative of d omega dt. And omega is the derivative of theta with respect to t. The integral of omega dt will give you the change of theta, and the integral of alpha dt will give you the change of omega. And that's all you need to remember here. So in the second case, you had to integrate the trend line, or sorry, take the derivative of the trend line in order to find alpha at a specific time. In the third part of the problem, you had to integrate omega, the trend line, in order to, and I should really call these alpha t and omega t. You had to integrate omega to find the change of theta, and then you had to convert to revolutions. And that is, there are 2 pi radians in 1 revolution. So you just can convert it either way. All right. And then this last problem before we go back is actually going to be using these ones that we talked about. So we're told that a computer hard disk, I guess I should say this really fast. If we look at these, just like with free fall, we have a theta initial and a theta final, an omega initial and omega final, an alpha and a t. We're going to assume that alpha will be constant in these problems. And then we have these equations. So let's think about these. A computer hard drive, I should say that we also should have R. Computer hard drive is 8 centimeters in diameter and it's initially at rest. Now the diameter of a circular object is R plus R, so D is 2R, and we can find R by dividing D to the half. In our case, 0.8 or 8 centimeters is 0.08 meters divided by 2. So our radius is 0.04. We're not going to be in centimeters. We are going to be in meters. So you better change that to R and put it in meters. Now, it's initially at rest, which means omega initial is 0 rad per second. rad per second. A small dot is on the edge. We accelerate with an alpha of 610 rad per second squared for half a second, and then coast for the next half second. So we're only going to deal with the first half second. So in the first half second, okay, and we don't know omega final. We don't know, there's a dot on this edge and it's going to spin around and around and around. But we're going to assume that it starts at 0 rads. And then we don't know how many it's going to end up with. Then we're going to do the second part of the problem. The second part's actually using. What is the speed of the dot at 1.0? Now, it's accelerating for the first half second, and then whatever speed it has at that point, whatever omega it has, it's going to stay at that omega for the second half. So we need to find omega final. And if we come back, we don't know theta. So if we look at this, we have omega final is omega initial plus alpha t. Omega initial was 0. So omega final will be 610 alpha times 0.5 seconds, or half of 610 is 305 rad per second. Why? What did I do? Oh, we want the speed of the dot. So we have this, right? But remember that V is R omega. So we need to multiply. We want to find V. So 0.04 times R305, and that'll give us the velocity of the dot. 0.04 times 305 is 12.2 meters per second. Sorry, I didn't read the question. Or 12 meters per second. So we found omega final, and then we found V from that for the dot, because the dot is at the edge. All right. Then we want to know how many revolutions has it turned. So in the first half second, we need to find theta final. Assuming that theta initial is 0, theta final is unknown, omega initial was 0, alpha was 610 rad per second squared, and t was 0.5 seconds. Theta final minus theta initial is omega initial t plus alpha t squared over 2. This is 0, this is 0. So in the first half second, it turned half times a half, which is a fourth. So that would be 610 times a half, times a half, times a half, 76.25 rads. Now in the second, from 0.5 to 1 second, in this amount of time, it had an omega final of 305 rads per second, and it was constant. Alpha was 0. And if alpha is 0, then theta final minus theta initial is omega times t, and t is going to be half of a second. So if we just want to figure out how far it turned in this, it would be 305 times another half, or 152.5. Add those two together, and we get 76.25 plus 152.5. I get 228.75 rads, or about 230 rads. How many revolutions though? So in order to get revolutions, I divide this by 2 rad, pi rad per rev. So divide that number by 2 times pi. And I get about 36.4 revolutions. It went around about 34 times, 36 times inside. And they rounded it to 36. Okay, so just make sure you know how to do those. They're going to come up more later. They won't be on our first exam, but make sure you know how to do it. And so now we're going back to a couple of projectile motion rules. And projectile motion is the big one. In projectile motion, we have usually some initial velocity at some initial angle. And the very first thing that we note is we can break this into an X and Y motion. So we can have V of X. Sorry, do that a little weird. We can have a V of X initial, which is our initial, and this is really our initial magnitude times cosine of the angle. And we can have a V of Y initial, which is our V naught sine. Okay, so the first thing you almost always have to find is V of X and V of Y initially. And they're whatever your launch or launch speed and launch angle were. Then we can break up our motion into Y and X. X initial, X final, V initial of X, V final of X, A of X and T, but there is no A X usually. So these are just whatever our initial. And we went over this in class, and we almost always have an X initial of 0. Okay, usually you can choose to start it at X is 0. In our Y, so our equations here, if we go back and look, we only have V naught of X, T. Another way to write that would be X final minus X initial is V cos theta times T. And we have that V naught of X is V final of X. Those just come from A of X being 0. In the Y, we don't have, or we have an acceleration of negative g. We don't necessarily know where our initial y is. Our v initial of y is v naught sine. But y initial, y final, v final. If it goes up to the top, v of y at the top will be 0 at maximum height. Our equations for the y direction are y final minus y initial, or v naught yt minus gt squared over 2. And again, you can insert v naught sine here. V final of y is v initial of y minus gt, and v final of y squared minus v initial of y squared is minus 2g y final. So we have 2 equations in the x. We have 3 equations in the y. We have no acceleration in the x. We have negative g in the y. We always start with 0. Basically, we start measuring x from wherever we start. But y, we might be at a different initial height. And so that's it. And you'll see, if you were in class on Friday, you already saw how this worked. But here, we're going to start with the following problem, which is a little weird. We have a plane that's initially flying at a speed of 200 meters per second in the x direction only. And it's initially at a height. Y initial is 110 meters. And it's going to drop a package. Now that package is going to have the same initial velocity and the same initial height. And when it hits the ground, it's going to have a final height of 0 meters. That's what we mean by 110 meters above the ground. We mean that y final is 0. So what we're being asked first to find is how far short of the package. So we're basically being asked that if this thing's dropped, where should we release it so that it lands exactly where we want it to? We're basically being asked to find what is x final. And if we do that, and just look at the following. X final, V initial of X, V final of X, which are the same. A of X and T, and then over here, I'm going to write the following. Just normally, how you will start all of these problems is by writing your variable, just like free fall. You might have to rewrite them every time you change something in the problem, like every time you try to find something new. But AX is 0, AY is negative G. Y initial is 110, and Y final is 0. X initial, I'm going to say, is 0, and X final is actually what I want. Now we get to the weird part. V naught is only in the X, and I don't actually have to find what it is. But if I assume that the angle is 0, because it's making an angle to the x-axis of 0, then I would get 200 cosine of 0, which is 200. V initial of y is actually 0. It's only moving in the x when you release it, and it's moving at the same speed as the plane. This is exactly like the free fall one where the balloon went up. We don't know what V final of y is, and we're not going to use it. We don't know time. Time is the same for x and y, but we don't know it. So x final minus x initial is V of x times t. And x initial is 0, so that's going to go away. I know this is 200, but I have two unknowns. In order to get rid of that, I need to find a way to find time. Well, thankfully, I have this. And I will tell you this, anytime you have y initial is 0 or v initial of y is 0, you're pretty much going to use this equation. And the reason why is that this term goes away and it's really easy to solve for time. Y final is 0, v initial of y is 0, I get negative y naught is negative g t squared over 2. These negative signs go away. If I multiply both sides by 2 over g, I get that t is 2y naught over g, or v of x times 2y naught over g. So x final is 200 times the square root of 2 times 110 over 9.8. And if I plug that into my calculator, 2 times 110 divided by 9.8, take the square root of this answer, multiply it by 200, I get 947.6, so about 948 meters. So what I've done is just like free fall, I wrote down x initial, x final, v initial, x, v final of x, ax, and t. And I wrote down for the y's. My equations in the x are only these. My equations in the y are only these. Then I determined that the initial x velocity was 200 by thinking about the problem or drawing the problem, and that my initial y value was 0, my v initial of y. Had it been at an angle, had this been flying up at an angle, I would have had to use trig to break them up into x and y, but I don't have to do that in this because it only has x, it doesn't have y. Then I solved for x final, which is, I had to be smart and read the question correctly, but what it was asking was how far away. So it was asking for x final. X final is vx of t, but I don't have t. So I had to use my y equation to get my t. And when I did that, I found 948. Okay. It's a pretty easy problem. Once you know how to do these, it's not a lot of surprises. It's more about setting it up and then knowing how to go between x and y, knowing what x and y are. So our next one is an Olympic shot put. Now the athlete throws 12.8 at 35 degrees. So our V naught is 12.8 meters per second. And it's at an angle of 35 degrees. But our Y initial is 1.8 meters above. So she's throwing it from her chest. If you don't know what shot put is, you take a really heavy little ball, you spin around and you push it away from you and it flies up and it lands some distance away. So the lands distance away. So how far? So we want to know how far this thing's going to go. This thing's going to leave her hand at that, and it's going to travel. Y final will be 0 meters. It's going to hit the ground. This is actually kind of a pain. X initial will be 0, and X final is unknown, but we want to know how far away. So again, X initial, X final, B naught of X, B final of X, A of X, and T. A of X is 0, T is unknown. We'll talk about the X in a minute. This is what we want. This is 0. We don't know this, and we don't know if we're going to use it. Now, Y initial, Y final, B initial of Y, B final of Y, and A of Y, and T. Y initial was 1.8. Y final will be 0 when it hits the ground. T is unknown. Y final is unknown. Y initial and V initial of X. So V initial of X is V naught cosine of the angle, or 12.8 cosine of 35. V initial of Y is V naught sine, or 12.8 sine of 35. And I can get those numbers and plug them in here. So 12.8 sine of 35 is 7.341. I would advise don't start getting rid of digits right away. It might round you weird. And 12.8 cosine of 35 is 10.4851. 10.4851. So around there. All right, now we know these things. We also know that we only have one equation in the X. X final minus X initial is V of X T, but again, X initial will be 0. V of X we know, we need to find T. T is going to be a little bit harder to find in this case. And the reason why is, if we just look in the Y, just treat this as a free fall problem. It starts at Y initial is 1.8 meters, and it lands at Y final is 0 meters. We know V initial of Y is 7.3418 meters per second. We don't know what V final of Y is. We want to find the time. And A of Y is negative G. So we have V final is V initial minus GT for Y. So both Y. And we have Y final minus Y initial is V naught of Y T minus GT squared over 2. And we have Y final minus Y initial is V naught Y plus V final Y over 2 times T. And the final one we have is V final squared minus V initial squared is minus 2G Y final minus Y initial. Now, in order to find T, you could do this and get the quadratic. I'm not going to do that. I'm actually going to do just an algebra step first. So V final of Y squared, I'm going to find V final of Y, is V initial of Y squared minus 2G Y final minus Y initial. Move that over and then take the square root. So I get 7.3418 squared minus 2 times 9.8. Y final is 0, so this is minus 1.8, or change it to a plus sign. So I have V final of Y, and I have to choose between a positive and negative. I know it's going to be going downward So this will be negative. That negative sign is important. Don't forget it. 7.3418 times 7.3418 plus 2 times 9.8 times 1.8. I get 9.4436 meters per second. Now that I have that, I can use this to find the time. So V final of Y minus V initial of Y is negative GT, or if I divide through by negative G, T is V final of Y minus V initial of Y over negative G. This is negative 9.4436 minus 7.3418 over negative 9.8. All those negatives are going to cancel and become positive. 9.4436 plus 7.3418 divided by 9.8. I get 1.7128. So the time is 1.7128 seconds. You could have done the quadratic. You would have gotten the same thing if you did it correctly. In order to find it, you couldn't have used this. You either had to find V final and then use V final to get the time using one of them, or did this as a quadratic, or you could have found the time up and the time down. There are multiple ways to find that final time. But now that I have it, 1.7128 seconds, my X final is 10.4851 V of X times 1.7128. So multiply that time by 10.4851 and you get about 18 meters. Okay, you get 17.96, whatever. So in this one, this is kind of an extension of the last problem, except this time we had to break up our velocity vector into initial X and initial Y. And unlike the previous problem where it was relatively easy to find T from Y, here, because Y initial and Y final are different, it actually became a big old pain. Well, they were different last time too, but it actually becomes a pain. You got to do some extra step to find your time. And it's up to you what that step is. Either do a quadratic, do the time up and the time down, or do the V final. If you do the V final like I did, the one problem you might have is the negative sign on the V final. Make sure you know it's negative. And this is our last problem. In our last problem, we have a kangaroo. A kangaroo can jump across the ground and it can go 9.4 meters. It leaves the ground at 22 degrees. So we know that it's going to leave the ground. We don't know what its initial magnitude is. We know that X initial is 0 and X final is 9.4 meters. So we know the angle and we know how far it can go. And we want to find its takeoff speed. So just looking at the X without thinking about the Y at all. This is 0. This is 0. This is 9.4. V initial of X is V naught cosine of the angle. And we want V naught. V naught is actually what we're looking for. Time we don't know. The only equation we have is X final minus X initial is V naught cosine T. So we want V naught by itself. X final minus X initial over cos theta times T. Okay. So again, we have to use T. And how can we help ourselves? Well, one thing that we note is Y initial is 0 and Y final is 0. And that actually makes everything super easy. Whenever that's the case, where it lands at the same height that it leaves at, you're going to see that that gives you a little bit of extra options. So this was V initial sine theta. V final is unknown. You could put that it's negative V naught sine, but whatever. We need to find T. We don't know V final. Y final minus Y initial is V naught YT minus GT squared over 2. Since these are the same, we get that this whole side of this equation is 0. And therefore, moving this over, V naught YT is equal to GT squared over 2. But you can cancel one of the T's. However, V naught of Y is V naught sine. Okay, so what we get is that T is 2 times V naught sine theta multiplied through by 2, divide through by G over G. I'm going to plug that in here. So I have that T is V naught sine theta with a 2 over G, right? And I have that V naught is X final minus X initial over cos theta times T. So for T, plug that stuff in. I get V naught is X final minus X initial over cos theta times 2 times sine of theta times V naught over G. Or rewriting this, multiply through, you get G times X final minus X initial over 2 cos theta sine theta. The V naught goes up, so this would be V naught squared. So take the square root. So that turns into that. One other thing we can do is 2 cos theta sine theta is actually sine of 2 theta if you want to do that. I personally don't. So I get V naught is square root of 9.8. Remember, X final was 9.4. X initial was 0 over 2 times cosine of 22 times sine of 22. Or you could put sine of 44, doesn't matter. You could change 2 cos sine to just sine of 2 theta. But 9.8 times 9.4 divided by 2. I forgot my, oh no, I got it done. 2 times cos of 22 times sine of 22. Oh man, 9.8 times 9.4 divided by 2 times cos of 22 times sine of 22. And take the square root. And I get 11.52, so 11.5 meters per second. Or 12, they rounded up to 12. But the idea here was, again, same thing. Now we don't know V naught. We have to solve for V naught. The other thing in this problem is that Y initial and Y final were 0. So that made it easy to find the time. And then we put the time back in. And we had to solve for V naught. So these projectile motion problems are very typical. I would say if you know how to do these, and you know how to do the ones that we talked about in the worksheet that we did last week, or the week before, I mean, you're good. There's not that many things, different things that you have to do. Make sure you know how to do these ones and you'll be fine for the exam. Again, as I said, the exam will have some projectile motion on it. It probably won't have very much rotation on it, but make sure you know how to do it. Because it's going to come up after the exam, we're going to do torque, and that rotation stuff is going to come up in torque more. So anyway, hope you've all had a good day off, and hope this is helpful, and I'll see you all tomorrow.